Hey everybody, we are here. Hey Andrew, hey Tabs. Ask the questions. I have a page written in my notebook filled of questions for you. Okay, let's hop over to those questions. Let's do it. Hey Perry, we are here. We're taking questions. Go ahead and ask those questions in the chat. So good to see everybody. Ask questions if you got them. Just give me any question you have and we will do that. I might also go over the Tabs. I made you a mod. I don't know why you weren't a mod, but you are now a mod. So put the questions in the chat that you have. I will start writing out some answers right here. I might also, what is power? 1 minus beta is power. Power is the ability to correctly reject the false null. So I want you to think about something here. When we talk about what power is, a type 1 error is rejecting let me just make sure. In a type 1 error, the null is true, and we reject it. So reject a true HO. That is a type 1 error. A type 2 error is fail to reject a false HO. So a type 1 error is when the null is true and we reject it. In a type 2 error, this is 2 right here, the null is false and we fail to reject it. There's your 2s for the type 2. So what is power? Power is the ability to reject the true null because power is the complement of beta. So power is the ability to reject a true null. So when we can reject the true null, that is a powerful test. I mean, sorry. I think I just misspoke because I'm talking about, make sure I don't misspeak today. Power is the ability to reject the false null. Please write that down right there. Power is the ability to reject the false null. I was thinking of the error up here, which alpha is when we reject a true null. Alpha is when we reject a true null, which is a type 1 error. That is, when the null is true and we reject it, that's a type 1 error. When the null is false and we fail to reject it, that's a type 2 error. And when we think about what power is, that is the ability to reject the false null. So let me say that clearly again. Alpha is when we reject a true null. That is a type 1 error. Beta, which is a type 2 error, is failing to reject a false null. And you can remember fail to reject the false null. 1 minus beta is power. That equation I have down there is literally power. And power is the ability to reject the false null. So when we're able to reject the false null, that is a powerful test. Power is the ability to reject the false null. Power is a good thing. Just so you can see right there, we've got alpha and beta.Ose are bad. They're not necessarily bad, but you don't want to make a type 1, you don't want to make a type 2. But, and I see practice test questions too. So let's see, does everyone understand what power is right there? Power is the ability to reject the false null, which is a good thing. You want a test that's powerful. You want a test that has the ability to reject the false null. So that is what power is. That is the equation for power, and the concept of power is the ability to reject the false null. So then we got questions here. Perry says, can you go over how to find alpha like question 2, part 6 on the practice exam? I think someone was asking me about that earlier. If I am correct, and correct me if I'm wrong, actually I've got the practice exam pulled up. I think I know which one that is, and I can do that one pretty quickly right here. Sorry, as I clear my throat, everyone. So here's the practice exam. And I'll zoom in on it in a moment here. This is question 2, part 6. Question 2, part 6. So this right here, I believe, is you're using a confidence interval. And use the confidence interval from part, okay. So what we have to do, this is a 93% confidence interval, okay, good. So since we've been using a 93% confidence interval, let me close off this stuff right here. I'll keep going through every question you guys have. Thank you for asking them all. If you build a 93% confidence interval, my 3s always look so bad. If you build a 93% confidence interval, that is the same as doing a two-tailed test. So this is a confidence interval right here, but a 93% confidence interval, we'll shade this in with some, there we go, so that way it doesn't cover it up. 93% confidence interval is the same mechanically as doing a two-tailed test. The does not equals alternative where alpha is equal to 0.07. So the alpha right here, this is the kind of total rejection area, is going to equal to 0.07. Reason is if 93% is on the inside, 7% is total on the outside. So that's the way it works right there. If you have 93 inside, it's 7% outside. And a confidence interval works mechanically the same as a two-tailed test with 1 minus confidence interval level alpha. So what did I just say there? Two-tailed test means the outside test when we're doing the does not equals test, which I've written right up there. And when we talk about 1 minus confidence interval level, well, 1 minus 93% is 7%. We generally write alpha as a decimal. You could say 7% alpha or 0.07 alpha. Good questions in the chat right there. And let's see. Keep asking those questions. I'll try to hit as many as I can. So I think I did Perry's. First question, can we assume randomization or does it clearly have to state it? We will state it in the questions. Great job, Tabs. We will definitely state it. We will make it very clear. I know my Pearson sometimes is like, assume randomization. We will make it super clear. We'll be like, we randomly select it. We try to make it as clear as possible. If you feel like it's not clear on the test, please ask. Please ask anything you think is not clear. There's a small chance that we might have to clarify something to all students, but if it's like a little like not clear, we generally just talk to each student. You are free to ask all your questions during the test. Raise your hand, ask a question. We like things to be as clear as possible. It is hard to write a test for everybody, but we look over it. We have multiple people look over it, and so that's our goal. Can you go over II on question 7 for the practice exam? Yep, let's do that. Let's do that. Question 7, which one's question 7? Is this question 7? I think nope, question 8 still. Okay, here we go. Question number 7, oh cool, I like this output. So this output right here is the two sample means output. Once again, let's know our tricks. We should know our tricks pretty quickly. One of our tricks is when we see this output, we should know this is a two sample t-test. You know it's two samples? Well, one, because you see t-test, so it's a t-test. You know it's two samples because you see here two groups. Now I know this literally says group 2 and group 1, but it could say male-female, it could say Britain, USA, we had that on another test a while ago, but it could say any two groups. It could just be, you know, Tennessee, Florida. It can be any two groups, and that makes it a two sample t-test. We can write the null and alternative just by putting a mu there and mu there. For those not knowing what I'm talking about, I'm literally saying I've written the null by going here and writing mu group 1 minus mu group 2, or was group 2 first? Well, darn. Use the order it gives you. Use the order it gives you. It puts group 2 first, put group 2 first, and then that equals 0. That is the null hypothesis. What is the only thing that changes when we write things out in mathematical notation? When we write things out in mathematical notation, the only thing that changes when we do the alternative will be the sign. I always say if you can write the null in mathematical notation, you should be able to write the alternative. So if we write the null out here properly, and this is not the answer for the question, but I'm just focusing it on this output, saying that you have a cheat sheet right there for writing the null and the alternative. Make sure you know how to write the null and the alternative, doing it in mathematical notation for the one sample t, the two sample t, the proportion test, and then the chi-squared you don't use mathematical notation on. Chi-squared is x is independent of y, x is not independent of y. I'll just do the full question right here because it's part 1 and part 2. The values for the upper and the lower represent the 95% confidence interval. What is the margin of error of this confidence interval? So when you look at this confidence interval right here, we want to know the margin of error of it. So the way to think about it visually is that the margin of error is half the length of the interval. Here's the lower, here's the center of the interval, and here's the upper. So what you're literally trying to find is you're trying to find half the length. Half the length of the interval is the plus or minus, which is the margin of error. That is a margin of error. So what we can do is we can take those numbers, subtract them, and find their margin of error. Now, since the numbers are both negative, it's not going to matter that I treat them as positive. We're just trying to find the difference between the two numbers. The difference should be about 6, a little less than 6 it looks like. And so there we go. The difference is a little less than 6. Does that make sense that between 1.4 and 7.3 there's a difference of 5.9? And then we take that difference, we divide it by 2, and we have the margin of error. So the margin of error here is 2.9552. Now you know you've done this correctly if you can take the number in the middle and add and subtract it. So let's see, the number in the middle is negative. We'll actually use the negative right here. So 4.42, and let's actually use the negative. And now what I'm going to do is I'm going to add to it, and now I get the lower interval. You're welcome. Always glad to help out. I want to make sure people see this. Does everyone see how I double checked my answer right here? I'm like, okay, if that's the margin of error, that number that's in the center, which is the difference, I should be able to add and subtract to it. So I can take right here and do the same. I can do 4.42, and I'm going to put the negative on there just to make sure this is correct. And then I'm going to subtract from it. And if you're thinking, what will I get? If I subtract the margin of error, I should get the lower. So when I subtract this, I should get negative 7.3752, and I get it. That means I've done it correctly. Think about ways to check your work. This is the margin of error for this question. And then the question in the chat was, can we do part 2? Let's do part 2 right here, and I'll keep taking all these questions. I might scroll back through to find them. What was the value of TT? Oh, that's a typo. Is that a typo we have on here? TT hat. Oh, I think you know what it is. I converted this to a PDF, and so or a PowerPoint. That's what I converted it to. So I converted it, and I think the conversion did something weird to it. It wants what's the value of T hat? Not T hat. It wants what is the value of T star? So what was the value of T star? What value of T star was used to construct this confidence interval? Report to 4 decimals. It's probably going to be close to 2, but let's figure that out. Okay, so this is the margin of error. Margin of error equals 2.9552. So we know what the margin of error is equal to, but now we need to know that the margin of error, I'm going to put it over here equation-wise, the margin of error is equal to T times S over square root of n. What's even better is I think we have the standard error in the output. So margin of error equals TSEY bar. You can do it. Let me just see. Oh, no, you have to know that that's the standard error. So you do have to know that for this one. You do have to know that this is the standard error. I think I remember people taking this test, and they're like, how do we find it? We don't have S and we don't have N. You do have to know that that's the standard error, and then this becomes a lot easier if you know that the standard error is S over square root of N. So this literally, that thing right here is S over square root of N. This number, I'm going to highlight it and make it super clear, that is standard error of y bar, which I've written down below, and that is also S over square root of N. That is literally what that solves to. It's just an abbreviation of it right there. And so by knowing that this is the standard error, we pretty much have it, 1.4713, okay. So let's go over here to the blue side, and let's write 2.9552 equals, and then we're solving for t, and 1.453, was it? Something close to that. 1.4713, okay. If I make an error, please tell me. Like I could copy number wrong, it happens. And so now I think we just divide. We just divide and we got it. So all we're going to do is just bring this over here to the other side and divide it. It's just going to hop over here to this side and we're just going to divide. So I'm going to do it in the calculator. I'm just going to get the t. But I'm just solving for t with the equation that I'm using right there. So the equation is going to be 2.9552 divided by 1.4713. Whoa, 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 I think I put an extra decimal. I know what t should be very close to. It should be close to 2. Whoa, come on, calculator, delete those things. Always kind of think about what it should be near. That's a trick I tell you guys to do. Like solve it in your head a little bit. If you think you're dividing, it's basically 3 divided by 1.5, so it should be close to 2. Always think about, well, what should I be kind of getting? What should it be kind of near? So it's 2.009 rounded, 2.009 rounded. It's basically 2, and interestingly enough, this is a 95% confidence interval, and 95% confidence intervals are basically plus or minus 2 Z's or T's. Not always, it depends on the sample size, the degrees of freedom, which controls it, the T, but with a large enough sample size, it approaches 1.96. Let me look at the additional questions. So that's how you solve this one right here. I'll move my head out of the way. I wrote kind of the equations right here. We also knew the margin of error, and we were able to solve that. This is a tricky one. It's definitely one of those 2-pointers that is hard to do. You're welcome, Lindsay. Glad to help out. Good question. How do you know which p-value goes to the alternative? Great question. Oh, we don't have any output right there with it. That's chi-squared stuff. Please note that that's chi-squared. I'm trying to find an output where we have different p-values. I might have to pull one up. Okay, cool. Here we are with some output that goes with the p-value. You should know instantaneously that this is a t-test, but I want you to see something. How many means are there? This is actually right here in this output. This is y bar. This is mu naught, because that's the hypothesized value. That is the degrees of freedom. This is the standard deviation S. And then we're missing this p-value right here, which will be 0.0066, if I'm adding it up correctly. So in this output, if we wrote the alternative does not equals to, it'd be this one. If we wanted to see if it was greater than or less than, it'd be those right there. So we have right here all of this good stuff. I hope this makes sense with what we have right here. We also have, it's not in the output below, but this is n, because that's the sample size, which gets us the degrees of freedom 27, because n minus 1 equals degrees of freedom for a one sample t. So that is the degrees of freedom. Kind of got a D looking good. But how do you know which test it is? You know which test it is by the way the question is worded. And do remember that you have the relationship that the p-values, the less than and the greater than, add up to 1 because you're shading both sides of the curve. It's like if you draw a curve out, and then I knew those would be behind me. I knew it right as I was drawing them. If you draw a curve out and you put, it's not the way I like to draw them. I like to draw them this way. Go here and go here. If you were to put a line right there, then the area below it and the area above it should add up to 100%. Then the way we do the two-tailed test is you simply take where that line was at and you reflect it on the other side. So my drawings might not be perfect, but if you notice, it should be double. So this one right here, let's put it, these two add up to 1 when you go above and below, which you're seeing over there on the less than and the greater than, they add up to 1. And this is 2 times the smallest. So it's got to be the smallest because you can't have a p-value outside of 1. So 2 times the smallest, which is what I did to solve for that p-value right there. I just did 2 times the smallest. And in truth, this one, the graphics over there should look, the less than test should be the smaller one. So let me draw what that should theoretically look like. Theoretically, I'll draw all 3 of them again for this graphic right here. The way, if we had distributions for this, it would look the following way. Since the less than is the smallest, we landed down here, and then I'll put this as my two-sided. So there's the two-sided test, there's the less than, and then there's the greater than. And so those are the associated p-values. I'm going to do one last thing right here. The less than and the greater than. The reason I'm drawing it this way is this is the first, this is the second, this is the third, this is the first, this is the second, this is the third. I want my drawings to be as accurate as possible so you can see that those are the graphical visualizations of kind of what the p-value looks like. It's a little bit smaller than that. I should have moved the red line further out. But you would get something similar to this graphically because you're graphing the area less than a result that had a negative t-score. This would have a negative t-score if we solve for the t-score. Some more answers in the chat. Let's see here. Tavs asks, you know how you give us that link with all the practical exam questions and went over them in depth? Which link? The answer you gave for number 8, part 1 is different in the video from what's written on the practice and key on the stats homepage. Does it move both answers except for 1? Which question tabs? Which question tabs? With all the practice exam questions. Which number 8, part 1? On this exam right here, tabs? What are all the conditions that need to be met for a chi-square test of independence? Condition 1 is random. We randomly select the data. Condition 2 is 10%. We take less than 10% of the population. Condition 3 is that we have expected cell counts greater than or equal to 5. So make sure you know how to find expected cell counts. And condition 4 is count data, which means both variables are categorical. And we'll do Tav's question next right here, which might be on this. This might be question 8. Is it question 8? Looks to be question 8. So you can tell that this is count data because, and we do, so let's check some conditions right here. and I had a different answer tabs, uh-oh. Well, I'll take a look. We'll do questions. I wonder what I have. I'll have to take a look at that video and see what I said at that time. Your instance view is different from what's on the practice exam key. What? We'll look at that here in 2 seconds. I'll have to look at that. So all of these expecteds right here need to be greater than or equal to 5. All of those values right there, that's expected cell counts, need to be greater than or equal to 5. That is, there's no real order to the conditions, but I like to say that's condition number 3. And so all of those need to be greater than or equal to 5. And then you might be wondering, is this count data? Yes, this is count data because it is categorical. Categorical is count data. Is it the null and the alternative? Oh, cool. Tabs, is it this one right here? What is the null and the alternative? Is that different? There can be different ways of writing this. Good, I'm so glad it's this right here. Yes, so there's different ways to write this. I like to use, and I probably said this in the video, did I say political party is independent of someone's age group? Political party, you can flip the X and the Y, it's no big deal, because saying X and Y are independent of each other basically means this is independent of this, and so if this is independent of this, then this is independent of this. So it's kind of like a correlation, like X is correlated with Y. Now don't use correlated, don't use that word here. But if you say, close your ears if you want. If you were to say X is correlated with Y, you're also saying Y is correlated with X. So in this problem, if we say X is independent of Y, we're also saying Y is independent of X. And so it really doesn't matter which one goes first because you're saying they're independent of each other. Like Brian's score is independent of Darren's score. So by virtue of saying that Darren's score is independent of Brian's score. So there is, and the graders should know that, we should make that clear to them, that if you say, and that's a good question, Sydney, you ask. In a lot of statistics, it will matter what is the X and the Y. And in this one, I would probably say someone's, I'm trying to think how I would say it to be more exact. Because what do X's do? X's explain, and the Y is what we want to understand, because we want to say, why is this happening? So we might want to understand someone's political party. So we might say someone's age group being X is independent of their political party. So I would probably, if I was doing like real, like deep statistical analysis on this, I would probably say someone's age group is independent of their political party. Because age group might explain political party. So the first one that does the explaining you put first, like does someone's age group explain political party? So when you think about it in the statistical sense, you have to think which one is the X, which one is the Y. Now in truth, if X is independent of Y, Y is independent of X, so that it's an acceptable answer to put either one first. It's kind of like mu1 equals mu2 or mu2 equals mu1, either way goes, so you can switch it around, it means the same thing. Can we go over and I think I'm going to keep going through the questions in order, and Mona Lisa will do yours here in a moment. Thank you for asking all the questions. We'll definitely do it. We've got tons of time left. Cool. If you have studied for a long time, done both practice exams, do you think we'll do well? Sydney, I would hope so, and I think you will. If you're understanding what I'm talking about now, then you'll definitely, I can't say definite, but I would hope so. If we did all 3 review assignments but did not get above 90 on one of them, will this affect our grade? It'll be dropped. Lindsay, it'll be dropped. When is it important for X to be before Y? It just depends on if you purposely have a certain X, you want to do the explaining. But in truth, when we write these things, X and Y can be flipped, at least in the notation. Like when we say X is independent of Y, Y is also independent of X. But that's not, don't worry, we'll try to make that as clear as possible on the key. Can we go over the contingency coefficient? It's easy, but I don't know what numbers to look at. The contingency table, cool. I love these contingency table ones because you can do a lot of practice on these if you just remember. I want you guys to tell me, Brian, this is the formula for what? You should know instantaneously. You should be able to tell me mathematically what that equals. No, not that. Oh, the one we'll do that one next. Awesome, Mona Lisa, we'll do that one next. This is just so if you can see boom, Perry knows that that's an expected because that's row total times column total over grand total. Nice answer right there. And that should equal 174.453. If you know things like this, then you can check your work. You can make sure you're doing it correctly. There's also a secondary check we've talked about. And please, if you're like Brian, you're going too quick, slow down or do this specific one, please ask. All of these values right here should add up to what? This is a secondary check. All of those values, if you add those up right there, should add up to what? This is one of my favorite secondary checks. They should add up to that right there. All those values right there, if you add up all the expecteds in a row, it'll add up to the row total because they have to. It's just the way the mathematics works. That's just a secondary check. For this one right here, I would still originally solve it. I would still do the original solve of this because that's the actual formula for it. I would do the row total of that times the column total of that, which this is the row total, this is the column total, and this is the grand total. Those are those right there. And so I think you guys understand these. This cell right here is the observed, and how do we know it's the observed minus expected squared over expected? It's a cell chi-squared. So the cell chi-squared is the formula observed minus expected quantity squared over expected. If you're unsure about these, I would maybe try to solve another one like this right here and see if you're getting the right answer for it. Just to be like, okay, am I doing the right formula for what I should be getting? And if you solve that 3.74, if you solve that one and you get the right answer, like if you're just a little bit worried and you're like, am I doing the right formulas? And if you get that answer and you solve that cell correctly, well then when you solve for B, you know you're doing it correctly. This one right here. So when we look at this graphic right here, let's see what we got going on. This graphic right here is, we see kind of a decrease. You know, just tell me kind of what's going on with people as they get older. And maybe it's easier to see this is the X right here and this is the Y because it's on the X axis. So if you're really worried, maybe look at the mosaic plot and maybe like age group, which is X here, is independent of someone's political party. So what do you notice about people's political party affiliation as they get older? Well, we're kind of putting something out here with A, B, C, and D. What is decreasing? The amount of independence in each age group is decreasing as someone gets older. Now, here's the hard thing, and that this is what confuses people about this question, is right here, a little hard to see what I'm highlighting. Yeah, we can see it. Right there, all those people are what? Every single person right there is what? With those people I've highlighted, every single one of those people is what? Every single one of those people is what? Every single one of them is 18 to 29. You got it. So now when we go here, you might think you want to go this way, but don't. Because now you just want to do this right here. Every single person there is 18 to 29, because all those people right there. And I've highlighted a what now? I've highlighted a what? Down here on what I just highlighted, I've highlighted a what? Think about what I've highlighted. I've highlighted a what right now? Let's see in the chat. I've highlighted a row. So we're going to go to the row percentage, and we want the row percentage of the independence, and we're going to look at this. And you notice we kind of have all the answers now. If we know what's going on, we just found all the answers. So we just found every single one of the answers for this question by selecting the right thing. Those are all the answers right there. They can be found another way. You could literally do the mathematical solve. You could say 209 out of 391, because notice how the 209, let's do that in blue, the 209 and the 391, like in the 18 to 29 age group, there is 209 out of 391 independence. So you could solve it that way, or you could use the output to solve it. There's a few ways to solve it. And so what I want you to think about is, does this right here look to be around 53%? Does that look to be about, and I'm not saying where it's at, but does that look to take up 53%? Does that look to take up 53% of the total area on that curve right there? And if that does look to be close to 53%, like as though this covers 53% of the up and the down on this, and then the next one should only cover a little less, 47 point, let's say 47, we'll round it. Is that 47%? And it should be. If you look at a visual with 37 and 28, 37%, 28%. So if those look accurate, you've probably done it right. If it looks like that's a little more than 50%, a little less than 50%, around a third, and a little less than a third. So you can see the decrease, and those numbers are highlighted in the row percentages. Does that help, Mona Lisa, help understand what's going on here with this output and figuring out the correct numbers from it? Will you go over number 9 through 10 and when to use what technique? Number 9 through 10, sure. Number 9 through number 10. Oh, cool. I like these ones. Yeah, this is great right here. And you're welcome. So glad to help you guys out. Yeah, this is really good review right here because we haven't talked too much about these. let's do a huge review on this. Okay. So what do we have for like one quantitative variable? So if you have one quantitative variable visually, you could do, here we'll go visual right here. And let's go test. So with one, trying to think of everything I can think of. So with one quantitative variable, you could make a histogram. You could make a box plot. You can make a histogram. You can make a box plot. You know, it might work. You know what I'm going to do? Since I'm writing so much, I'm actually going to write it out. I'm actually going to insert. Let's just do it normally. Okay. So one quantitative variable. So you got histogram, box plot, trying to think what else, stem and leaf, and t-test on the mean. So let's put that right there. Let's change colors on that. Cool. And now let's go here with one categorical variable. Right here you have, and I'll give you guys some example problems of this. You have a bar chart, you have a pie chart, you have one proportion test on the proportion. And there's other graphics, I'm sure, but those are the main ones right there. Let me zoom out a little bit and write some more down. And this is just a short list of ones off the top of my head. We're still that color. So let's put in, now we have two quantitative variables. And so if we have two quantitative variables, think about what we can do here. So you should try to think of some stuff as I'm mentioning this, like what could we do? We could do a scatter plot, we could do regression, and if we do regression, we can do correlation. I finally know how to spell it. Well, I guess I do. I always put like one R. So two categorical variables. Two categorical variables, we were just doing that a second ago. This makes count data. So we should be using a mosaic plot. Sure. Contingency table. Okay, that is two categorical variables, and then we have categorical X and quantitative Y. So here we have a side-by-side Also, we have decision trees. I didn't put decision trees on here, but I think this is a decent list of a lot of the techniques we've done. There is the document that covers this, the tools and techniques document. But here, let's do an example problem or two, and then I'll take Kelly's question here next. If I were to say, I want to collect data on, let's say, I want to take data on your grade on the exam, and so like your grade is in an A, B, C, D, or F, your grade on the exam and your class level at UT, what would we do? Now grade is going to be noted as A, B, C, D, or F. That's your grade on the exam and your class level like freshman, sophomore, junior at UT. You would look through and you'd be like, okay, I'm probably looking for a certain what. If it was like, let's analyze someone's grade as in A, B, C, D, F on the exam and their class level at UT. Good question. Kelly and Brianna, you are correct. When we would use pivot tables and charts, they can be used for pretty much everything. So Kelly, great answer. So let's put this right here. Can handle, I think we have just enough room. Can handle large amounts And so generally these right here, this is like my super Cliff Notes version of it. Pivot charts / tables, decision trees. Decision trees and all that, they can handle, so if we were to write a question for like a decision tree, I'd probably write it something like, a baseball team is trying to analyze if they are going to win their games. So that's their why variable, if they're trying to understand why they're going to win games, because it's why are we going to win, that's the why variable. They collect 20 different variables and they want to figure out what's most important. Does everyone see that when we talk about the decision tree, it generally is handling larger amounts of data? So a baseball team is trying to figure out why they're winning, if they will win games and why they are winning games. They have 20 variables collected. What is a way for them to figure out some sort of statistical model? And so if they have a whole bunch of data, if you remember how a decision tree works from the project, you kind of just put all your data into it and it figures it out. So if you remember literally just doing split, the tree figured out what variables to use. So think back to that, you'd be like, okay, wait a minute. This is not like we have a one y variable, so this is multivariate, we call it that, multivariables. And so now we're going to analyze a whole bunch of x variables. So if we were to say they want to visualize a lot of their relationships quickly and easily, we'd probably suggest pivot tables and pivot charts to them if they want like a lot of different visualizations. Especially if it's undefined what their x's are, then pivot tables and pivot charts can do a lot of different visualizations. They can pretty much, that's really when we get to the hard points of writing questions sometimes, because pivot tables and pivot charts can do so much. That's why we teach that section. Does that help better, Kelly, understand kind of these ones down here kind of handle larger amounts of data, and pivot tables and pivot charts, they can do like histograms, they can do time plots and all that stuff. What sort of question would you ask about the business analytics lecture? So there's usually we go for an overview of it. We usually ask about like things like, so would you guys remember the one store found out that girl was pregnant, the teenage daughter was pregnant before the parents even knew. So that was Target found out about that. You also have things like Moneyball. Moneyball changed the game of baseball by using analytics to actually make data-driven decisions in baseball. They totally changed the way baseball has been run. Additionally, you've got descriptive, predictive, and prescriptive analytics. Just trying to think of as many things I can cover in that as quickly as possible. But business analytics is a huge field. The growth in the field has been insane. Like we see other majors popping up sort of like it. Other people are like, we have to have people understand how to analyze data. Data is used in every discipline. I mean, I'm not trying to sell the major right here or sell the idea of data, but data is knowledge, and being able to extract that knowledge from the data takes a person who has experience working with it. So the better you are working with data, it really helps in any field. Additional questions, feel free to ask them. Let's ask another question here. A student wants to make a visualization of the test scores that their friend got. And they're going to take like the actual numeric grade. A student wants to make a visualization of the test scores that their friend got. So of their friends, like they have 40 friends, they want to make a visualization of the scores of their 40 friends. What would you suggest to them that they make? So they want to make a visualization of the test scores that their 40 friends got. And we're talking like 50, 80, 90, 100, so we got some good scores in there. But a student wants to make, yes, box plot would work. Yep. Do you remember bar charts and pie charts? I like to say you can make a pie chart of your favorite bars and a bar chart of your favorite pies. So those are both categorical. And think about it, favorite pie is categorical, favorite bar is categorical. Like the question, what is your favorite bar, what is your favorite pie, are categorical questions. And those, Zach and Perry, you're both right. Those are both answers right there. Stem and leaf is also acceptable. So you can do some weird ways of asking these questions, like which of these is something they couldn't make? And then the histogram, box plot, and stem and leaf, and dot plot. We have dot plots in here this semester. So let me throw dot plot on here. Dot plots are just, instead of the bars, you make dots. Dit plots, dot plots, dot plot. So I don't expect dot plots. I don't like those. I'm just mentioning it. I don't even know why I put it on there. If a student wanted to see if more than half the students passed the class, so passing and failing is literally passing and failing, what could a student do to see if more than half the students passed the class? What could the student do? So the first thing you have to do with these questions, you have to say like, what is being analyzed? You have to say, Okay, they're analyzing a categorical variable, then what could they do here? I'm hoping we get them graded by Friday. I'll be careful. So you're close. You're thinking of the visualization. The visualization would be a pie chart. You are correct. We could visualize that with a pie chart. The visualization, hypothesis test of a proportion, yep. They would be testing 0.50, so the null hypothesis would be that the true proportion of students who pass the class is 50%, and I think I said they want to see if more than half pass, so the alternative would be greater than. Project 3s were supposed to be graded this morning. There is still 70 for my class outstanding, or 71 last time I checked. There was 104 yesterday, and then 71 this morning, even though I was told they'd be graded, and if you emailed me, I know a few people did, I was like, I am holding my breath because I was told they'd be graded this morning at the latest, quote unquote. I am very sorry. I might step in and get that fixed up. We'll be having the past. Yep, you can definitely do that, Lindsay. You can definitely swing by, look at your exam. I will be here. I will be gone Friday, and feel free to ask any exam-related questions. I'll be gone Friday through Monday, and I'll be getting in later Monday, late Monday, I think. But I will be here Tuesday. Why does chi-squared not use the left-tailed test? Great question. Why is chi-squared a one-tailed test? Chi-squared is just a one-tailed test because of the way it works. The smallest difference, mechanically speaking, when you do the chi-squared, the main components of the chi-squared are this right here. These, oops, that was a horrible X right there, horrible slash. There we go. So all of these cell chi-squareds right here are going to be the components of the chi-squared. When we sum them up, we get the chi-squared test statistic, which is the Pearson chi-squared test statistic. If we were to have a chi-squared of 1, it would look something like this. It's a very, very skewed distribution. And what we do is we plot the sum of all these. So you'd literally take the sum of all them and you'd plot it here. So the question is, why is it just a right-tailed test? Why don't we do things like the left-tailed test? Well, think about this. The smallest difference you can get between these is 0. So when we do this, we're trying to figure out the probability of our results or results more extreme. And results more extreme in this instance would be the probability above the chi-squared we have, because this would be differences that are bigger. The chi-squared takes into account the absolute value of the difference, so it doesn't matter if the difference looks like this or if the difference looks like this. And I said absolute, but it squares it, so I think that's a better way of understanding it. So if you were to have example 1 or example 2 with a similar difference, you would get the same chi-squared. Since both these graphics are kind of similar in their shift, if they have the same amount of data, then they would get the same chi-squared because you're squaring the difference. The key right here is it's the difference squared, so all these differences will become positive, so you're not looking at kind of a negative positive because they'll generally kind of average out if you don't square them. And then we standardize by the expected. So the reason it's a greater than test is because the smallest possible difference is 0. And if we had 0, all of these observed and all of these expecteds would be equal to each other. And if they all equal, then they're pretty much independent, and the graphic would look the following way. If they were all exactly equal, we would get something very much like this right here, because there'd be no deviation between the cells. So there would be exact independence. So this is where X is completely independent of Y, and then the more deviation we see, then wouldn't the left-tailed test show if the data was overfitted? Let me think that over. Really good question. Let me think, Daniel. Well, this is not like fitting a model. So when we talk about overfit, a lot of times we talk about that we have something that is definitely coming. Yeah. When you talk about overfitting, usually we've overfit a model to the data to make predictions, and I don't think that would apply here because we're not really making like we are. Overfitting is when it doesn't generalize to new data. At least that's the way we usually talk about overfitting, is when we make a model on training data and it doesn't generalize well to a new data set, and that's what we usually call overfitting. You might be using it slightly differently, but that's how I generally talk about overfitting, is when the model does not generalize well to new data. It's overlearned. And actually, a model that, and there's a lot, I'll just mention this real quick. A model with a much higher chi-squared would be more likely to be overfit. Down here would likely be underfit. So good question. Definitely making me think today. It's exam day. I'm not supposed to think. My brain's supposed to be turned off. So great job, Daniel. Have you already gone over multiple choice question talent review? Just confused on how to find which tool is the best? Let's do that. Cool. You are a regional manager of 5 large grocery stores. So you're regional manager of grocery store A, B, C, D, and E. You let each of the managers of the 5 stores make their own decision who to hire. Since the 5 stores are within 50 miles of each other, you would expect the ethnic background of the employees at the 5 stores to be similar. So we have ethnic background. Ethnic background is going to be like all these different groups right here. Group 1, Group 2, Group Group K. Which tool or technique would you use to address this question? Let's take a look. Both of these variables right here are categorical. So since they're categorical, what do we get? We get the chi-squared test of independence. Always try to identify what types of data you're dealing with. This is, can we go over true or false? Yep, we'll do true or false here in a second. Great questions. And then we have questions on notation too. Does that make sense here, Daniel, that I've identified what kind of variables I'm dealing with? This would be different grocery stores, grocery store A, B, C, D, E. I just gave them random letters for their names. And then we also have different ethnic backgrounds, so just different groups of people. So it's categorical, and that is one of the conditions for the chi-squared is count data. So this would make count data, which is the literal condition and when we use it. So it's a bivariate analysis. The reason other ones would be wrong right here is the histogram is quantitative only. This one's categorical. This one is bivariate quantitative. Hypothesis test for a population mean, that is one quantitative variable. And then Pearson's correlation is this right here. In truth, any question that would be simple regression could also be done with Pearson correlation. Regression is fitting a line, and correlation is looking at the positive, negative, linear relationship, because Pearson's correlation is linear, but both those could be used interchangeably, so we probably wouldn't put them both on a question unless it were to be it. This is the visualization of a quantitative variable. This is a test on a quantitative variable. So identifying, and here's the good news, if you identify that at least one of those is categorical, then it should eliminate to chi-squared. So I really like this one, and great question. Hopefully we go as in-depth as possible on these, but good question right there. Let's see here. We've got the true-false people want to do, and I think I broke it by turning it into this. I changed it. Okay, power represents the probability that we correctly fail to reject a true null hypothesis. No. If the null is false, we should reject it. We made it look a little bit nicer, Sydney. Everything on the formula sheet will be on there. We made it look just a little bit nicer for this, so we just kind of like updated just the way it looks, kind of just made it look a little bit nicer with the wording. But everything on there is on there. So if you look at the formula sheet, you should get it. And power is the ability to correctly reject the, let me read again. Power represents the probability that we correctly fail. So no, we should correctly reject a false null. So this is false right here. Power represents the probability that we correctly failed. No. Power represents the probability of rejecting a false null, correctly rejecting a false null. If based on the sample set of data, you change your level of confidence from 90 to 95, okay. The resulting 95% confidence interval is considered less precise. That is correct. It is more, wait, it's probably nobody. Let me head back to here real quick. They'll leave a message if they really need me. It's like all of a sudden, like, what's going on, Brian? So I'm like freaking out. If based on the same set of data, you change your level of confidence from 90 to 95, it's less precise. From 90 to 95 will be less precise. That is true. It'll be more confident and less precise. So as confidence goes up, precision goes down. Confidence and precision are inversely related, so higher confidence level, less precise. And what do I mean by less precise? Imagine I told you the test will take about 45 to 50 minutes. I'm about 10% confident. But if I go, and so here, I'll do that one next right here. And I think, Dylan, you might be right. I'll check that in a moment. A p-value represents the probability of seeing the results you saw or results more unusual than that, assuming the null hypothesis is true. Yep. P-value is the probability of our results from our machine having a random chance variation given the null is true. That is, and if it looks super accurate and you don't see any errors with it, good. The only way to decrease the probability of a type 2 error is to increase the probability of type 1 error, false. Three things are alpha, sample size, and effect size. We don't control effect size, but type 1 is this. That's the type 1, but we can also change the sample size. In the business analytics class, we talked about how Target used data to determine if a local customer is about to shop there. That is false. We talked about how they found out a girl was pregnant before her parents knew. That's what we talked about. I was trying to post it. It's not there right now, but what was effect size? Effect size is the difference between the null and the truth. An effect size that would be easier to notice. Imagine, I always use the example where I play my brother in basketball or I play Dwight Howard in basketball. So you could watch us both play for the same amount of time. You could watch me versus Dwight or me versus my brother. It'd be easier to tell that Dwight is better than me because the null hypothesis for both in test 1, and this is test 1 right here, right? Test 1 is Brian equals Darren in skill level. So the null hypothesis would be that for test 1, and test 2, it'd be Brian equals Dwight. So we write here the most preposterous thing ever, Brian equals Dwight Howard's skill in basketball. So which of these would be easier to reject the false null with? Because that's what power is. It's the ability to reject the false null, to correctly reject the false null. It'd be easier to reject the null that Brian and Dwight are the same. You could watch us for the same amount of time, and you could use the same standard. You could say, okay, if they win by 10 points, then I'll say this person's better, and that's kind of like your alpha level there. It's like, at what point will you reject, which is alpha. But Dwight would just totally destroy me in basketball, and that's the effect size. The effect size is the difference between the null and the truth, and the null is that we're the same skill, but the truth is Dwight is way better. Now, my brother is also better than me in basketball, but it'd be easier to see this when I play Dwight. I think there was a lot of notation questions. What is y bar, p hat, and mu represents? So let's do those right here. We have here y bar. That is the sample mean. We have here S. S is sample standard deviation. We have here mu. Mu represents the true mean. Mu naught is hypothesized true mean. Please note, and I try to make this clear, whenever you put like a p naught, that would be hypothesized true proportion. And so this is all quantitative right here. I didn't write out everything, but that's just like a starter guide to notation. And I always say, like, what is count data again? Count data is when we have two categorical variables, such as like political party and gender or political party and age group. Those are two categorical variables. Has to be two categorical variables. Nice job, Zach, in the chat. Love it when you guys are answering questions for each other. So I try to do as many questions as I can and keep firing those questions. I'm gonna go for about 10, 15 more minutes. There's a formula sheet. It's pretty up to date. It has everything on there you should know. And we just made it look a little prettier for this test. Can we go over the true false? We did the true false. I think that's it. Keep asking. Could you go over how to find the p-value questions like 6 or 8? Where do we ask p-value on 6 or 8? Let's find that out. Oh my gosh, zoom in way too far. Do we ask a p-value here? So this one wants you to know where the p-value is at. Can you write? Yeah, we'll do that next, Elizabeth. We'll go to some formula. Hopefully, the formulas might look weird on this because when it copies it, it looks weird. So maybe it'll be weird. Moving around the pencils. Okay. The Pearson has your p-value. The p-value is the one with the Pearson. This value right here is the sum of all the cell chi-squareds. That is the p-value. So we're definitely going to reject the null hypothesis. And I would say that there is evidence that age group is not independent. Age group is not independent of someone's political party, i.e. knowing someone's age group gives you information about their political party. So I didn't Do we have audio now? We do have audio. Hey, everybody. Okay, we are back. Sorry about that. We were on 2 bars when I started up, and it's funny, when you go on like 3 bars to 2 bars takes a long time. 2 bars to 0 bars is like, it's like that. So we went for about 30, 40, or no, we can go in an hour. Oh, man. Can you explain the sample size assumption again? The 10%? Lily, can you... Are you talking about the sample size assumption that, well, we need to randomly sample and we want to sample less than 10%? And then, so we did the p-value on this one. How do we find the p-value on the chi-squared? Lots of questions coming in right now. And then there was a question about 6. And so I'm doing them all in order as best I can. As many questions as I can do before. Is this question 6? Which one's question 6? We're at the null alternative. Looks like we're testing one mean right here. So... Okay, wait, here we go. Based on your answer to part 2, would your decision be to reject or fail to reject the null? Was this I think this is a greater than test. Don't quote me on this. Can people confirm in the chat? I think we're going to see if it's greater than. Let's see. We need to know the alternative for this. So the emergency room believes that the amount of time it takes to get is 2 minutes. So they believe it is 2 minutes. Now that sounds like a does not equals test right there for the moment. A nursing student was asked to randomly select incoming patients over a 2-week period and figure out how long it takes to get the answers to the questions. As long as they're deemed non-appropriate, they're asked in the waiting room. The time it takes to complete the initial question has come under scrutiny. The emergency room believes that the average amount of time it takes to get the questions answered is 2 minutes. To get these initial questions, 2 minutes. Wait, here it is. Most emergency room employees believe it takes longer. Boom. That is a key word right there. It takes longer. I kept reading this question over because I was like, I think it's a greater than question. So when I see this right here, it takes longer, that's going to tell me the alternative. Please notice that they're trying to imply an alternative right here. So the null will be the following. The null hypothesis will be that the true mean of time it takes in the emergency room is 2 minutes. The alternative hypothesis will be that the true mean of time it takes in the emergency room is greater than 2 minutes in the waiting room. Please note that I had to read the question to make sure I knew which way to write the alternative. So now a lot of people wonder, and this is a great question, a lot of people are asking this via email, but I keep asking the questions. If you don't know the question, ask it. And that's what I always say, because don't worry, if you're asking about someone else's, and when you ask it again, someone else will be like, oh, I was wondering that, I bet. And someone will say, oh, I was wondering that in the chat, because that is a question a lot of people are asking me. So we're gonna skip over calculating the test statistic right here. We're gonna hop right to figuring out if we reject or fail to reject the null. We are going to reject the null hypothesis, and we're going to use this value right here as though that is the value. So what we would need to do, and this is what I would do, on this test question, I would probably draw a little graphic over here like this. And I'd go here and I'd do the following. 0, 1, 2, 3. Now we landed right over here. And so with this area, this is the p-value. So my p-value, because I landed at, that's the value I landed at, that's where 3.21 is at. So I landed right there, and so how do I know I reject the null? Can anyone tell me on the normal curve, because this is actually on the normal curve, how much area would we have above here? On the normal curve, that is 2.5%. Above there, as in this value above here is 2.5%. And if you notice, the p-value is much smaller than that. So yeah, if you don't have the graphic, you're fine. Basically, this is a large z-score, or excuse me, t-score. Brain jumped out of my head for a moment there. This is a large t-score, and so this would lead to a smaller p-value. So the question wants you to notice that we would reject the null right here. And reason being, and what does this mean? Well, this means we have evidence that the amount of time it takes is longer than this because of the small p-value. And if you notice a lot of the problems I solve, I always try to draw a little graphic of what I'm going to get. So this would be definitely reject the null. And if you look over here, the degrees of freedom would be df equals 31. So this is a t with 31 degrees of freedom, which is generally a decent amount of degrees of freedom to make it almost like the z and the t. Close enough that it is true that we would reject the null hypothesis. A little bit of a tricky question there. We do like to show applet pictures too. A lot of people are asking, how can you do that? Like, how can you do this on the test? We can also show applet pictures and be like, which applet picture would you use? And I kind of like that way better, because then it's like, what if you actually had the applets, you could solve it. So great questions right there. Does that help with understanding how you could maybe understand if you're rejecting or failing to reject the null right here? Do a little drawing, think about what you would do next. And we kind of want to maybe see if you're on track with what to do. State, so this one says, well, the p-value right there, and state the remainder. We have evidence that the true waiting time that people are taking in the emergency room is greater than 2 minutes. You don't have to draw. Which part of it do you want me to go over more? Be like part 3 or part 4? So this question says, briefly explain your reasoning. The p-value has to be below 0.05 in this one, because the z statistic is very large. Probably what you could say here, and it might say this on the key, the z statistic is more than 2 or 3, or excuse me, the t, I keep saying z, sorry, it's right for the test. The t statistic, which you would go through in this problem and solve out for the t statistic, the t statistic is, as stated in this problem, that's what it's using just as a placeholder. And since this is so very large, larger than 2 or 3, then we're going to get a p-value smaller than the alpha of 0.05. And so I would definitely draw this out. That can really help. And this is probably one of the, I would say it's a very tough 2-point question. Now, what we always do, and I'll state this, we always have these questions contingently graded. I say to my graders, when a student gets to this question right here where they have to state the remainder of their conclusion, I say grade contingently, because your conclusion right here would depend on rejecting or failing to reject the null hypothesis. So when you get to this, think about all you have to do right here. Since you rejected the null, try to put before this, go here and write, I reject. I have evidence. So what would you say? I reject that the true waiting time in the waiting room is 2 minutes. I have evidence that the true amount of time people wait in the waiting room is greater than 2 minutes. So using this right here, listen how we read it. I reject the null hypothesis that the true waiting time in the room is equal to 2 minutes. I have evidence that the alternative is true, that the true waiting time in the waiting room is greater than 2 minutes. I see a lot of people asking questions. Could you please explain how to know if the count data condition is met? Count data is when we have 2 categorical variables. Nice job, Dylan, in the chat. He already answered that right there. Will the formula sheet on the exam be labeled the same way? Yep, it'll be labeled the same way. We just made it look a little bit nicer, just cleaned it up a little bit. We made the formula sheet look the same way. How do you know where to start? Where the alpha value in part 3 of number 6. Is that the one we're on right here? This one right here? How do you know where to start? That we wouldn't know directly from this. But we always try to like this, and I'll basically give some keys to the test right here. When we usually give you a T or Z, if we give you a T or Z, we try to make it extreme. In truth, I would want this one to be a little bit bigger. Like sometimes it's not as big as I like, but what if we were to give you a T of like 0.45? Think about where that would land on the curve. If you had a T of 0.45, that would land right inside between 0 and 1. If this is what the question gave you, you would land right here, and I want you to tell me, does this look to be more than 5% of the curve? So with a T of 0.45, would that be more than 5% of the curve shaded? And I think that's one of the fairest ways to do the question. If we were to give you, instead of the T right there, a T of 0.45, then up here you would see that you would fail to reject the null. And so the t is very small, making the p-value very large. That is way more than 5% of the curve. So we would definitely, if this was what it gave you right here, you would definitely fail to reject the null. So I always support doing a drawing. I know a lot of times with applets, it's like, well, we'll just let the applet do the work. But then imagine you have to draw it out too. So critical values, T's and Z's will be given. Yes, Joanna, you are correct. If you have to make a confidence interval with a critical value, we will give it to you. And we could show you applet pictures and say, which of these applet pictures would you use, and use the correct value. So we might show you applet pictures maybe with like 95% confidence interval shaded or a two-tailed test, but we can show you applet pictures and be like, use one of these applet pictures. We like doing that, especially for normal curve stuff or for Z's and T's. What if we are given a chi-squared value? Yeah, chi-squared we don't like to do that with because the chi-squared is a weird looking curve. It's a right-skewed curve that becomes normal after about 30 or 60 degrees of freedom. And then the formula for its center is the degrees of freedom, and its variance is 2 times the degrees of freedom, and square root of variance is standard deviation. Ignore everything I just said right there. We don't like doing that with the chi-squared because of the way it looks. We could technically show you applet pictures, but we oftentimes like to show chi-squared output on the test. We like to show, definitely if you notice a lot of my review videos, I've been stressing the output to know kind of what the output for the chi-squared looks like. Question 5, part 3 and 4, does that make sense there, Daniel? I kind of talked quickly. But we would generally not ask you to compute kind of a chi-squared was unusual because of the way the distribution is. It's a different distribution. The z and the t are almost identical, especially after large enough degrees of freedom. The chi-squared is kind of its own thing. And then we didn't do f. I never said f distribution. Question 5, part 3 and 4. Let's do like 2 more questions. Then I'm gonna get some food. Thank you everyone for being here, and thank you everyone for working hard on the test. I know everyone's been working really hard. So, oh cool, this is a great one to end on. We got type 1, type 2 error. The margin of errors. Okay, let me do that really quick right here. We're gonna end with this question, and we're gonna write out the margin of errors. Okay, let me write out margin of errors. Margin of errors on this test will be things like, that's the margin of error right here. And then the other margin of error is everything after the plus or minus is the margin of error. Brain's slowing down. That's df right there. That's a subscript df. And cool, I didn't run into myself. This 1 squared over n1. That is a margin of error right there. Remember, margin of error is everything. If you see a plus or minus, beta is the probability of making a type 2 error, and type alpha is probability type 1. That is correct. Great job, Dylan, in the chat. Nice job, Dylan. Let's make Dylan a mod. Dylan's been in here all the time. Dylan, you get mod status. You get mod on the channel. Add mod, Dylan. There you go, Dylan. But these are the margin of errors. It is everything after the plus or minus. If you see plus or minus, that means a margin of error. So you're welcome, Dylan. So let's hop back here and let's do this last question, then I'm gonna get some food. Okay, think about this. What do we wanna be nice to students. We don't wanna say students cheat unless we got evidence that students cheat. So a type 1, type 2 error. In a type 1, the null is true and we reject it. In a type 2, this is a 2 right here and this is an F. In a type 2, the null is false and we fail to reject it. Those are the literal definitions of a type 1, type 2 error. Once again, in a type 1, here's your 1, the null is true and we reject it. That'd be the wrong thing to do. In a type 2, the null is false and we fail to reject it. So these are the important things we should remember like that. It's memorization, just put it in your head. So then we have to think here in a type 1, with any test, there is always, I'm gonna read it down here. So I don't read off these screens, I'm so blind. With any test, there's always a risk of making the wrong decision to describe a type 1 error in context. So in a type 1, so this is talking about a type 1 right here. This is true. It is true that the student did not cheat, but we are going to reject that and say that they cheated. I'd literally write that out. So it is true that the student did not cheat. Just in a type 1, the null is true. We know that. In a type 1, the null is true. Write out, it is true that the student did not cheat, but I am going to reject that and say that they cheated, because if we reject the null, we say we have evidence for the alternative. So, with this right here, let me see, I might run by my office and see. Don't count on us having Terry bring some, but watch out, because we might have a bunch of people saying, I need a calculator. So try to grab one. So we've got an hour and 30 minutes, 90 minutes, 91 minutes. But it is true that the student did not cheat, but we're gonna say we have evidence that they cheated because we're gonna reject the null. So a type 2 is the reverse. In a type 2, the null is false, but we fail to reject it. It is false that the student did not cheat, so they actually did cheat. It is false that they did not cheat, so they actually did cheat, but I'm going to fail to reject that. Oh, you're welcome. Thank you, Joanna. But I'm going to fail to reject that and say that I don't have evidence that they cheated, because in a type 2, the null is false, but I fail to reject it. So it is false that the student did not cheat. The student actually did cheat, but I'm going to fail to reject the null. Condition, I'll finish this question, and I'll mention those again. And I do have a conditions video up. What is the symbol used to identify the probability of making a type 2 error? Type 2 error is this. This is type 2. This is type 1. This is power. It's chi-square, but it has nothing to do with any of that. This is a formula we don't use. So we've got here type 1 error is alpha, type 2 error is beta. Power is 1 minus beta, which is the probability of correctly rejecting the false null. That is correct. One time I misspoke earlier. And chi-squared is chi-squared. That's used for categorical data, which is a great way to end. Daniel, great job in the chat right there. Randomly collect your data, 10%, less than 10% of the population is sampled. We have here expected cell count is greater than or equal to 5, and count data, meaning both variables, is categorical. What is the difference between writing out the decision versus writing out the conclusion? Feel free to, it's not clear during the test, feel free to ask us. Usually we say, well, thank you, Dylan. Usually we say, put your conclusion in context of the problem. That's usually what we say. So if we say put your conclusion in context of the problem, that would be things like, we did one earlier where it's like, oh, it's right here. State your conclusion in context of the problem. We have evidence that the patients are currently waiting on average more than 2 minutes. So that would be kind of, I rejected the null, which we set up there, reject the null. But since I have rejected the null, I have evidence that the patients are waiting on average more than 2 minutes in the waiting room, that the true waiting time for the patients is more than 2 minutes. Think, I reject that the true waiting time is equal to 2 minutes. I have evidence that the true waiting time is greater than 2 minutes. So it seems that their hunch was right, that the true waiting time people have in the waiting room is more than 2 minutes on average. Any last questions? You guys got another quick one? I really appreciate it, and thank you guys so much for all the hard work this semester. We'll hopefully have these graded up this week. That's our plan, and projects will be graded really soon here. I've got some stuff in place to make sure they get graded, and thank you guys so much for all your hard work. I am going to head out, grab some food, and we will see you guys here in a little bit. So thank you guys very much. We got to see Crash one more time. Got to see Crash. Whoa.